Swayam Prabha. Digital India. Educated India.
For rigid rotor, we have discussed how one can set up Schrodinger equation starting from the square of angular momentum operator, and we have worked out the phi dependent part, and we have given you the answer for the theta dependent part. And the answer we have discussed is the wave function essentially is spherical harmonics. Theta phi is equal to the theta dependent part multiplied by phi dependent part, and now we can talk about what is J and what is M. This capital M is something that arises out of solution of your phi dependent part of the equation. Remember, capital phi turned out to be A multiplied by e to the power I m phi. What is A? We will work out in the assignments. What does M stand for? It stands for the z component of angular momentum. What are the allowed values? 0, plus minus 1, plus minus 2, and so on and so forth. Yeah. What is J? J is another quantum number that comes when we work out the theta dependent part. Also, do not forget that J, the theta dependent part and phi dependent part are related by this m square. So, it also gives us a limit to the value of capital M. Okay. So, J turns out to be 0, 1, 2, 3, 4, 0 and positive integers, and the limit of capital M turns out to be J, alright. So, if J equal to 3 for example, you can have M equal to 0, plus minus 1, plus minus 2, plus minus 3. So, we have 2J plus 1 values of M. Okay. We will come back to this once again when we talk about hydrogen atom. The theta dependent part is basically a constant multiplied by an associated legendary polynomial in cos theta. Okay. That is what it is. So, the theta dependent part is a polynomial and the phi dependent part is an imaginary exponential term factor. Okay. Now, what happens when we try to find the energy? For that we go back to total angular momentum. We are going to discuss angular momentum and its component in a little more detail in the next module. For now, just believe me when I write, when the square of angular momentum operator operates on the spherical polar harmonics, when it operates on spherical harmonics, I get back the same spherical harmonics wave function multiplied by its corresponding eigen value h cross square multiplied by j into j plus 1. So, total angular momentum is h cross square multiplied by j into j plus 1. How did we obtain the Hamiltonian? We obtained the Hamiltonian by dividing the square of angular momentum operator by 2i. So, that 2i is essentially a constant for the molecule. So, I can very simply write this, the Hamiltonian is L square by 2 mu r0 square. So, this is the wave function and we know that this L square operates on the wave function to give us. Now, I have written out h cross and I have written explicitly h by 2 pi square of that multiplied by j into j plus 1. Okay, this is a Schrodinger equation. Now, I simply divided by your 2i. Let us go back on that a little bit maybe. this is L square. From there we go to Hamiltonian, and to go to the Hamiltonian I have simply divided by what we had in the denominator. We have 2 mu r0 square. So, that gives us h square by 8 pi square mu 0 square. So, a constant multiplied by j into j plus 1 multiplied by the wave function, that is your Schrodinger equation. This is the eigenvalue of energy in joule, where j is equal to 0, 1, 2, 3, so on and so forth, as I had said. Alright. So, what do we learn from here? Before going there, this is something that I write essentially because I am a spectroscopist. Generally spectroscopists do not want to work with joule, they prefer centimeter inverse, especially when working about rotational spectroscopy. So, generally we convert this to epsilon j is equal to h by 8 pi square IC multiplied by j into j plus 1, which is simply multiplying by hc, and that is in centimeter inverse, and it is simply written epsilon j equal to b into j plus 1 centimeter inverse, where b is h by 8 pi square IC. This is called the rotational constant. So, this is where we are, right. Let us take a look at this. First of all, b into j plus 1. What is the minimum value of j? 0. What is the minimum value of energy then? 0. So, remember, for a quantum harmonic oscillator energy could never be 0, because the oscillator, if it is at rest, then the position is 0 plus minus 0 x, delta x px is also 0 plus minus 0. So, delta x and delta px are both 0, and that violates uncertainty principle, which is not allowed. Here what happens is, let us say this is my rigid rotor, okay, this has a tail. Let us say this is my rigid rotor. So, it can rotate in any direction, any theta phi can be spanned. Let us say it has come to rest. Okay. It is true that the uncertainty in angular momentum is 0. But what is the uncertainty in position? For that we will need to know delta theta and delta phi. Well, uncertainty in theta is, well, theta can be anything, right. It can come to rest here or here or here, anything, anywhere. So, uncertainty in theta is effectively infinite. Of course, it cannot be more than pi, but in that domain that is infinity. Uncertainty in phi can be again anything between 0 and 2 pi, yeah, which is infinity. So, even though uncertainty in angular momentum is 0, uncertainty in the positional coordinates is infinity. That is why the day is saved, and a quantum rotor, rigid rotor, can come to rest anywhere in space. Okay. Uncertainty principle is not violated, that is point number 1. So, minimum rotational energy is 0. Now, look at this, epsilon j equal to b into j plus 1, b equal to h by 8 pi square IC. So, what is j, what is the next level after 0? J equal to 1. When we put j equal to 1, what do we get? Maybe I can just write that. The minimum rotational energy is 0, we have written. What happens when, maybe we will write like this, these j values are already given here, is not it? What is the energy corresponding to j equal to 1? The energy corresponding to j equal to 1, you can put j equal to 1 here. So, j equal to 1, j plus 1 equal to 2. So, the energy turns out to be 2b, right, 2b. What happens when j equal to 3? You can work that out, j equal to 3, j plus 1 equal to 4. So, sorry, why did I go to j equal to 3? Well, it is okay, 12. So, 12b. I missed j equal to 2 here for some reason. Okay. So, you can work out the energies and the values are all written here. Now, let us work out something interesting. What is the energy gap between J equal to 1 and J equal to 0? Obviously 2B, because this energy is 2B, this energy is 0, difference is 2B. What is the energy gap between J equal to 2 and J equal to 1? 6B minus 2B. So, you can write it here, the energy gap is 4B. What is the energy gap between J equal to 3 and J equal to 2 levels? 12B minus 6B, that is 6B. You see a pattern coming up. J equal to 4 and J equal to 3, 20B minus 12B, that is 8B, and J equal to 5 and J equal to 4, 30B minus 20B is 10B. Okay. Not very difficult to work out really, right, because what I am trying to work out is delta epsilon for, since I am a spectroscopist I always write in terms of spectroscopy, J to J plus 1 transition, that turns out to be equal to what? You can work it out, B into, instead of J I will write J plus 2. So, J plus 1 becomes, well, J plus 1 becomes J plus 2 and J becomes J plus 1 minus B J into J plus 1. So, J plus 1 is common and inside the bracket you have J plus 2 minus J. So, it is 2B into J plus 1. So, the energy gaps turn out to be 2B into J plus 1. Okay. So, energy gap keeps increasing as you go higher up the ladder in rotational energy manifold. Does it remind you of something? Reminds me of particle in a box, that is exactly what happened there also. Now, this has profound implications in rotational spectroscopy. Turns out, and I will not derive it here, once again it is there in our molecular spectroscopy lectures. One can work out the selection rule. The selection rule turns out to be delta J equal to plus minus 1, which means that rotational lines, in rotational spectra lines will occur at intervals of how much? The first one will occur at 2B corresponding to the delta J equal to plus minus 1, right. So, you can go from 0 to 1, that energy gap is 2B. Then you cannot go from 0 to 2, but you can go from 1 to 2, remember delta J equal to plus minus 1. So, that energy gap is 4B. Then again you cannot go from 1 to 3, you can go from 2 to 3, that energy gap is 6B. The next one is 8B, next one is 10B, and so on and so forth. So, what you end up getting is spectra with lines that are equispaced for a rigid rotor. So, what we get is equispaced line spectra. How is that useful? It is useful because that difference in energy is 2B into J plus 1. No, sorry, difference in energy is not 2B into J plus 1, difference in energy is 2B, difference in lines, difference in energy of lines is essentially 2B. So, once you record a spectrum from the spacing you can work out B, and if you work out B then you can work out this, this is B. So, H is known, pi is known, C is known. So, knowing B you can work out I remember is mu R0 square. Again if you know which molecule you are working with, mu is known. So, you can figure out what R0 is. from the spacings you can find out R0. What is R0 for a diatomic molecule? It is a bond length. So, this rotational spectroscopy provides a means for determination of bond length. That is the application of the rigid Rotor model that we have discussed so far. Of course, it is a simple model, life is not so simple. So, it is very possible that the rotor is not rigid, the molecule while rotating does not keep its bond length constant, but all that comes into the domain of little higher level quantum mechanics and spectroscopy. We will not go into that right now. It is discussed in our molecular spectroscopy course of course. For now we close this discussion, but it is not completely over, because remember we still have to discuss angular momentum in a little more detail, and in doing so we will learn some elegant features of quantum mechanics in the next module.